Hello everyone, I am Shovardo Pal, and in this video we are going to do result analysis and report generation of WR90 waveguide using HFSS. Now in the last video I have shown how to design the rectangular waveguide using HFSS. So we are going to do analysis of these parameters in this video. I will be showing you graphs of each and every one by one after this, and I will show you how to generate the reports. Let's move to HFSS. As you can see, I have this model which I prepared in the last video, and today, as I said, I will be showing how to generate the reports. I have already created a report in PDF format already, and I will explain you how I created this report. So first, before doing anything, what we need to do is have any structure along which we are going to measure the different components like electric field and magnetic field and other variations, as I have shown in the slide. So for that we need in this case we need a line along which we are going to measure the different parameters, and I'm going to draw this arbitrarily at first. So after 1 second. So after drawing, what we need to do is click on this and adjust this parameters accordingly. So I will set the point 1 to be of width by 2 and height 1 by 2 and 0, and the ending point should be similar to one, the first one, and the ending is be length. Sorry, the ending one should be negative length because the structure is extruded along the negative direction. So after clicking, you can see that the structure has been drawn in the center. uh, yes, as you can see, this needs to be in the center of the structure so that we can measure different quantities along this structure, along this line. Now let's see what we're going to do first. This is the structure, and these are the proper different HFSS properties that we are using in this structure. This gives the dimensions of many various structures of various blocks used in this video, and this is the actual diagram which shows the characteristic impedance of the structure. I will be showing this part in the later part of the video. Let's now first look at the solution frequency. We will be calculating the solution frequency of 10 gigahertz. This can be verified using by going to over here in the HFSS part and going to analysis. In the setup section part, if I double click, you can see that the solution frequency is set as 10 gigahertz, as I have shown in the PDF. And we are also doing a frequency sweep from the range 5 to 15. We can set the frequency sweep. I have shown in the last video, but I'm showing you again by clicking on the add frequency sweep, and after adding the frequency sweep we will be having this thing. And in this part you can see that it's from 5 gigahertz to 15 gigahertz, and the sweep type is fast. So the first case what we're going to do is we are going to have a short circuit condition in the second port, which is a lumped port. As you know that in the lumped port case we can vary the impedance according to our need. So for doing the short circuit, what we're going to do is just head over to the excitation section in the port 2. This is the port 2, as you can see. So in the port, so what I am going to do is replace the values with a very small impedance. Here 0.001 micro ohm is being used, so I'm also going to use that 0.0001, and the reactance should be 0 for short circuit, and micro ohms is set. As for short circuit, it ideally means zero impedance, but it's not possible in this software, so we are going to set this a very low value. So after setting this, I have changed the impedance. As you can see in the port 2, I have changed the impedance. And after that, what we're going to do is we're going to plot this electric field vector along the transmission line accordingly. And for plotting this, what you need to do is just click on this part. This is validates the design, and click on the second part, which starts the analysis and solution setup. So I am going to click on this solution analyze all part, and after clicking, the solution will take time a few minutes. I will be clicking this thing. I have clicked it and the solution has begun, and I'm going to pause the video and come back after the solution has been completed. Alright guys, the solution part is complete, and before going into the result, what I want to show you is that in the radiation box, what you need to do is the cuboid that we have used in the last video during the design, the Z size was 2 length plus 2 times of thickness, which is not to be the length should be minus length, but addition should be the Z position should be 0, and changing that will cause error in the solution part, because the ports should be at the boundary of the radiation box and not in radiation box. So if you error, then change the values accordingly, and we'll show you the results one by one. For the first electric vector around the transmission line, what we're going to is first select this line, which is the poly line, we have arranged this right now, and click on sorry, yes, the is plot fields and electric. Then what we do is plot the vector along the line. The frequency that we're going to use is last adaptive frequency. 1 second. Yes, the frequency that we're going to use should would be of let me check in the solution part what frequency should be used. So there is no frequency, and then we can just go to this 5 to this, and then just use the frequency of 7 gigahertz or 6 gigahertz. I'm going to choose uh 8 gigahertz. Let me just choose last adaptive and 10 gigahertz, and if this, and after this solution part, we will be having the vector distribution. As you can see, we have the distribution right on the screen, and you can copy the image and paste it in your according to your need. And in the PDF part, as I shown, our desired electric field vector along the transmission has been achieved, and this is the thing. Okay, so the next part is electric field. Then the magnetic field along the waveguide transmission line. For that, what we need to do is click on the polyline, plot fields H and vector H. The vector frequency should be 10 gigahertz. Click on that, and after that you can see there is second vector which have been plotted. Let me show you. Yes, this is the electric field along the transmission line, and this is the vector representation. And after that, what we need to so is the electric and magnetic field, as I shown that I just enable both of them. you will be able to view both of them at the same time, as you can see in the diagram. Yes, both the vectors have been plotted simultaneously. Now after that, we are going to see the magnetic field distribution along the transition line, and by not vectorial, we are using the magnitude form. So for that, what we'll do is, just a second, let me check. Yes, the study of standing wave reflection coefficient VSW at terminal transition line. Okay, short circuit, open circuit, and this is the standing. Okay, for viewing the uh, electric field, magnetic field distribution and electric field distribution along the transition line, what we do is, uh, just to go over the section which is fields, and click create field report rectangular, and after that a plot where geometry should be of polyline 1, and the frequency should be the last adaptive, the point should be 1001, and for viewing the magnitude electric field along the line, along the line, we can just click this and create new, and after that you can see report have been created, and this is very much similar to shown in this report. And similarly you can also plot the electric field. This is the electric field and this is the electric field, then we can also plot the magnetic field similarly. This is create field rectangular plot. The geometry should be poly, the point should be 1001, and magnitude of H, which is presents the electric the magnetic field along the geometry. So I'm going to create new report. After the magnetic field have been plotted, and see it's very much similar to the one shown in this report. Then I'm going to do is electric field, as you can see, and but you can add pointers to the graph according to your need. As you can see, we can just click on the marker and add marker based on the 2 points, as you can find for the lowest and one for the peak. The rule, the thing is, the distance between the uh, peaks and the distance between the two is known as the is to be of lambda 4, which is the guided wavelength, lambda g. And if you calculate the distance between the two, this m2 and m1, we will be able to find the guided wavelength similarly. So thing is the VSWR versus frequency. For that, what we're going to do is results, create a model data report, rectangular plot, the VSWR. This should be the domain should be a frequency, because you're going to analyze the thing along the frequency domain from 5 to 15 gigahertz, and just click new report. For every report showing, you can just take the screenshot, or just use the snipping tool to take the screenshot and paste it in accordingly. This is the VSWR one strip, and this is a little bit different because of I think the short circuit condition. Okay, so now going to use the reflection coefficient versus frequency for plotting the reflection. What we need to do is go to this solution rectangular plot, and S11 you should be plotting for, so you can choose the S11 parameter, and this shows the reflection coefficient. Yes, that is may not be actually perfectly same for both the, but it depends very much on the geometry and the kind of is that we're using for the plot. In this cases the graphs have been plotted for different frequencies and the different characteristic impedance as well. So by calculating the distance between the two as shown in the electric field distribution graph, you can tell the guided wavelength, and the distance between peaks is known as lambda g by 2, and you can find that also. Okay, then you can also find constant using the formula 2 pi by lambda g, and for that you calculate the uh, beta factor, beta by that formula. Then after you can write the observation part, and similarly for other conditions like open circuit, we can just do one thing, that is write the excitation part, and on the second port, not the first port, second port, we can just change the values. For open circuit impedance should be a very high. I am here assuming 10,000 ohm. So 1 2 3, and this is giga ohm. So, and the reactance 0, reactance is 0, and what when you changing the values, these graphs become invalid, and you calculate the using analyze all again. So I will be coming back after the analysis. So the result has completed, the solution part is completed, and we can now see the plots. This is the electric field plot along the polyline that we have created along the distance, that is like the distance like this, and you can change the marker positions as well according to your need. As I've shown in the earlier part of the video, this is the magnetic field versus distance plot. This is also varying like that, and you can see that open circuit case, the magnetic field is at the far end of this waveguide, and for short condition we will find the electric field is 0 at the far end of the transmission line. This is the VSWR plot, and the VSWR is voltage standing wave ratio. And copy these graphs according to your need and paste it in the S11 parameters are known as the reflection coefficient parameters, and it shows how much of the wave is being reflected at different frequencies. So as I have shown in the short circuit and open section, similarly you can also change the impedance of the two accordingly, and find the different distributions at different impedances, the characteristic impedance and arbitrary load also. For finding the characteristic I'm going to show you how you can find that. What you need to do, go to the result and solution data. That is, this will open, and you need to check this part which is not. You can see the Z naught is showing right now, and at 5 the Z naught is 243 reagist, and this is the uh, reactance. So you can see, as you can see, the characteristic impedance is being calculated, and you can put this value in the port 2 to the different field distributions at characteristic impedance condition. And arbitrary, you can put any arbitrary load at the port 2, which is a lump port. And for when you are left, you can similarly calculate different frequency distributions and lambda g guided wavelength at different conditions accordingly, and you can analyze the performance of the transmission line at different conditions. Similarly, you can also find the characteristic impedance, as I said. For the guarded wavelength versus frequency, you can I'm going to show you how you can plot that. For that, you need to go to results and solution model, solution data report, the plot, and here you can see there is also lambda versus frequency, and you need to new report, and after that the report will be generated solution. This thing is very much similar but not exactly same. It depends on various other parameters also, so you can test according to your design. So this is imaginary beta, imaginary gamma, which is also known as the beta, which is the propagation, the transmit the alpha is known as the attenuation constant, and it is propagation constant. Sorry, beta is known as the phase constant, as I know. This is the phase variation over the frequency. You can also plot that using the same method as I have said now. You can head over to the results, create model report, rectangular plot, and gamma. The every part of the gamma is uh, one second. Yes, the imaginary part of the gamma is known as beta, which are uh, the phase constant, and the real part of the gamma is alpha, which is the attenuation constant. You can plot accordingly, according to your need. So after that, to plot the variation of lambda g square versus the lambda the wavelength square inverse, and find the cutoff frequency of the waveguide. And if you calculate accordingly, you will find that the cutoff frequency for WNI around 6.57. You can try it yourself. Similarly, the graph will be like that. I need to find the cutoff frequency at this point, placing a pointer, and using this formula you will find the cutoff frequency. So after analyzing all the different loads and from the different fields of the line, we can come to the conclusion or observation that for short circuited load, the electric field at load end is zero. It's very obvious, as you know. And for short circuited load, the magnetic load end is not zero. It is at its peak. For open circuit load, the electric field at load end is zero, and the magnetic field at load end is zero for the open condition. For matched load, for that is the replacing the load with the impedance, the most of the wave will be traveling, and the less part of the wave will be reflected back. And for arbitrary load, the minima is shifted according to the load. You can actually find the arbitrary load value by the shift in minima by using the Smith chart method. The cutoff frequency of W190 as shown how to let will find that it is very much close according to theoretical value, and this is the proper analysis of the W190 guide, and I have shown you how to generate the report of the waveguide in your lab reports and other things. So prepare accordingly, and if you need any other graph, then you can also create as shown you. That. Thank you.